Good morning, everyone. We're going to go over this lesson on connecting plate boundaries with earthquakes, volcanoes, and we're also going to talk about hotspots, which is a unique type of volcanism on Earth. We have this really nice GIF of a volcano going off. That's always nice to look at. All right. So, just a quick review about plate boundaries and how we know where plate boundaries are. Again, it's all about the earthquakes. The earthquakes basically tell us where the plate boundaries are. But also, it has to do with volcanoes too. Volcanoes also mark those boundaries. So, volcanoes tend to occur along convergent and divergent plate boundaries. So, just a quick look here. This is a kind of a cool GIF here. You can see a convergent plate boundary. We see oceanic crust, which is more dense, diving underneath the less dense oceanic crust. And you can see, again, it's an animation. This is not what's actually happening, but it's a cool animation showing magma generation. So we're generating magma, and that magma is less dense, so it rises and creates a volcano. That's one place where you can get volcanism. Also, divergent plate boundaries. As divergent plate boundaries form, as the Earth splits open, you get magma shooting up, and you do get volcanoes. You do get lava pouring out at divergent plate boundaries too. Transform boundaries do not form volcanoes. There's a really old movie called Volcano. I think it's an early or mid-90s movie with Tommy Lee Jones. Really old movie, and it's actually about a volcano forming in Los Angeles, which again is completely impossible, but it's a good movie. It's ridiculous. There's a scene where a building falls down. It's ridiculous, but it's a fun movie. Anyway, all right, so let's talk about how melt is generated. When we say melt, we mean liquid rock. How do you melt a rock? And actually, as it turns out, it is really hard to melt rocks. If you were to attempt to melt a rock on Earth and you didn't know what you were doing, you wouldn't be able to do it. If you had a kiln, if you had an oven that could increase the temperature to incredible temperatures, you would still not be able to melt a rock. Rocks resist melting. So how does the Earth do it? Well, there are a couple ways, but the way we'll talk about is, again, this is a bit beyond the regions, but it is quite interesting. You can see here where in this diagram is very helpful here. What's happening is, it's pretty cool. Ocean water is, touching the oceanic crust. And that ocean water is actually finding its way, creeping down into the rocks, deep into the oceanic crust, moving through cracks. And what's happening here is a process called hydration. The minerals in the oceanic crust are actually taking on water. But that's kind of a weird process. The crystal itself, the mineral itself, is becoming hydrated. So it's structural water. It's water that's sitting in the crystal structure, if we can kind of imagine that. And so we have hydrated minerals here. And over long periods of time, right, it takes a long time for this to happen, but slowly but surely that oceanic crust dives deeper and deeper and deeper. And what actually happens is the heat causes a dehydration process. So now all of these hydrated minerals now release that water. And when you release that water into the crust above it, into this crust here, when you add, now this is a little weird, but when you add water to the rocks above it, those rocks are super, super hot. But by adding water, you actually cause melting, which again seems so strange, because if you were to add water, wouldn't that cause it, the rocks to cool down? It's actually the exact opposite. It causes them to melt, and that melt moves up and forms volcanoes. That's called dehydration melting. That's one way that melt on Earth is generated. And here is the diagram again. Much bigger. So yeah, that's one way that melt can be generated. It's dehydration melting, and it's a dehydration of minerals that were originally hydrated from water on Earth. Okay, we're going to take a quick tour of Google Earth. I want to show you all of the places where this dehydration is melting going on, and I just want to show you some relationships between a convergent plate boundary and where the volcanoes are in relation to a convergent plate boundary. We're going to start over here. This is the west coast of the United States. This is Oregon, Washington state area, and right along here is your trench. It's not a very obvious trench, but there is, I'll show you some other trenches that are much more obvious, but there's a trench right here. So the Juan de Fuca plate, it's a very tiny plate. This is actually the whole plate right here. Its boundary is here. This is a divergent plate boundary, and it kind of ends up here. So this tiny plate is smashing into the North American plate, and you can see, even from this view, a line of volcanoes. I want to make that very clear. It's a line of volcanoes, and here it is. We have Mount Rainier, Mount St. Helens. I want to say this is Mount Hood. I can see the volcanoes because they have these white caps on top of them. They have glaciers on top of them. So there's a line of volcanoes going all the way down here. Even into here maybe a little bit. Okay, so this plate's going underneath. It's causing melting. And we have a whole bunch of volcanoes. Here is Mount Rainier with its glaciers on top. Very, very pretty. But also very, very, potentially very deadly. Alright, other places where you can see this. Here's a really nice convergent plate boundary. Very, very obvious. The trench is very pronounced. Very, very pronounced. And one thing I want us to appreciate too is here's the trench. And then adjacent to that, we can see a line of mountains. This is the Andes Mountains that are forming from this collision. And they go all the way down here. Anywhere with this collision, we get mountain building, and we get also, you can see all the volcanoes. We have a line. And I can pretty much follow that line all the way through. All the way through. I'll just zoom in just to show you. We have some, it's not loading very well, but we have a volcano over there. My internet's a little slow right now. All through here, volcanoes, just a line of volcanoes moving all the way through the Andes Mountains. So that's one other place. Now, another type of or another situation I'm going to show you is well, I'm going to back up for a minute. So this is ocean crust colliding with continental crust, and we have a trench that's formed, okay? A very obvious trench. Here's another one. We have oceanic crust colliding with continental crust, and we have a line of volcanoes all along there. But you could also get ocean crust colliding with ocean crust, and the most famous of that is, we'll start here. That's fine. Right here we have ocean crust, the Pacific plate, colliding with the Philippines. Actually, what plate is this? Off the top of my head, I can't remember what plate it is. I have to go to the reference table. But you can see right here, here is the oceanic crust. It's slamming in. Here is your trench. Here's the Mariana Trench. The Mariana Trench is super deep. It's crazy how deep it is. And you might ask, well, where are the volcanoes? Well, you can actually see them. They're all along here. These are Pacific Islands that are formed by, volcanism. And this is called an island arc. Island arc volcanism. If I were to zoom in on these, I'll just zoom in. You zoom in. There it is. There's the caldera. There's the volcanism. If I go over here, we have a nice volcano over here. We have a cloud on top, it looks like. Okay, island arc volcanism. Again, just to appreciate the geometry of this, because that's important. We have a trench, and adjacent to that, we have a bunch of volcanoes. Now, if we go to a place that's we're more familiar with, maybe you've been on vacation there. It's a very popular vacation spot. These islands here, I'm actually going to turn them on. I'll turn on the labels. These are famous island names. St. Lucia, St. Vincent and the Grenadines, Grenada, Barbados, Dominica, Guadalupe, Antigua, and Barbuda. These are all very famous locations that people go vacation. Yeah, I'm going to turn it off for a minute. So here's your convergent plate boundary. The trench is not that obvious at all. But these are all formed by volcanism. Volcanoes form these. Again, see that arc and how the arc matches the arc of the convergent plate boundary, okay? So yeah, that's something I really wanted to show you on here. Just the relationship between the trench, and one more I'll show you that's particularly famous in the United States. This is the Aleutian Trench. These are the Aleutian Islands off the coast of Alaska. And we have a very clear trench structure, and we have a bunch of volcanoes. We have, extrusions happening. All of these were formed essentially by volcanoes, spewing up lava over very long periods of time, forming an island arc. Okay. The Ring of Fire. This is definitely something you learned about in 7th grade. The entire Pacific Ocean basically is covered with convergent plate boundaries. They're actually missing one right here. But basically, it's one huge ring of fire, lots of convergent plate boundaries. So they call it the Ring of Fire because there are volcanoes that are surrounding this entire area. So the Ring of Fire. Also a great Johnny Cash song. All right, so mental hotspots. This is extra weird. So a mental hotspot is basically a violation to the rules, or the predictions, I should say, that are set up by plate tectonics. Because plate tectonics basically says, okay, we got a bunch of plates, and the plates are colliding, and we got earthquakes at those locations, but we also have volcanoes at those locations. But a hotspot, though, really, in a lot of cases violates that rule. Because if you look at the Hawaiian hotspot, it is nowhere near a plate boundary. Yet there is essentially a volcano there that's always active. It's always spewing something. In some cases, it's more violent than others, or it's more destructive than other times. And that's intraplate, meaning inside the plate volcanic activity. It's a mantle hotspot. And there are a whole bunch of them all over the reference table. We have Hawaii here. Yellowstone's a famous one. And again, notice how it's pretty close to the plate boundary, but it's not on the plate boundary. It's not adjacent to it. The Galapagos one is pretty close to a divergent plate boundary. The Canary hotspot is not near a plate boundary. So again, it kind of violates the rules, or the predictions, rather, I should say, of plate tectonics. And the way a hotspot forms is actually kind of cool. Just, give me a minute to explain. It is a little different than normal volcanism. So the way it works is there is a plume, or kind of a stream, like a river, of magma that is always spewing up. It's always there. It's always active. And the plume itself, this river of magma, does not actually move. So the plume itself keeps its position. But the oceanic plate is what's moving. So the oceanic plate is moving over this river of magma, essentially, this plume of magma. And as the plate moves, it creates a volcano. And then it moves again and creates a new volcano and creates a new volcano. So these volcanoes here used to be over here, but they've since moved. And so this one used to be active, and then it moved, and then it became dormant and died out. And this one was active, and this one was active. And then, so currently this one's active. Once this plate moves a little bit to the left, a new volcano will form next to it. So the plate moves in the opposite direction of the apparent motion of the plate. I'm sorry, of the volcano. And it actually works a lot like a Hershey Kiss machine. It's a good example. So this is a Hershey Kiss machine. It's actually called a Hershey Kiss because the machine is quite literally kissing or touching the conveyor belt. So the conveyor belt is an analogy for the oceanic plate and how it moves. And you can see how the kiss machine does not move. So that's like the mantle plume. It doesn't move, but the conveyor belt does move. And that's creating a chain of Hershey Kisses, or in the case of the Earth, it's a chain of volcanoes. So here is the Hawaii chain. I'm going to go to Google Earth because it's way cooler. All right. And here's the chain. And the current location of the magma plume is right here. Kilauea. Kilauea is, if this could just load, that'd be great. It's very high resolution. So this is the crater of Kilauea. You can see lots of basaltic, right, dark colored, lava flows all over the place. It's really everywhere, actually. And this one's currently active. Give it a couple million years, this one will go dormant, and there'll be a new volcano next to it. And we can actually predict where it's going to be, right? Because it's a line. So we could predict it's going to be somewhere maybe over here, depending on the situation. The other islands of Hawaii are dormant volcanoes. They were formed by volcanoes, but they're dormant. And this chain goes all the way back. They're actually very pretty locations. We get lots of coral reefs here. They're called seamounts. Goes all the way back. And actually something really cool happens. You can see a kink. A kink in the volcanic chain. That is evidence that the plate changed direction. So the plate in the past was moving in one direction, and the plate shifted directions, which is mind-blowingly cool. And you can see the original source, where it all started a long, long time ago. So that's the Hawaiian chain, and there's one other famous chain, the Tonga chain, a chain of volcanoes here. Okay, the Tonga chain. Yeah. So hotspot volcanic chains. And as you might expect, the age of the rocks gets older and older and older the farther away you get from the source. So the rocks on the island of Hawaii itself, the actual Mount Kilauea, those rocks there are in some cases 0 years old, meaning they were just formed very recently. On Maui, 0.8 million years old. Oahu, Honolulu, 3.7 million years old. If we go back really, really far, right, 20 million years old, 43. So this hotspot chain's been going on for a while, which means that hotspot, that river of magma underneath the Earth has been active for at least 60 million years. So these hotspots just kind of stay in one spot. And last thing here, a graph showing distance from Kilauea and the age. And it's very clear. We can add a line in here, a very clear trend line showing that as distance from Kilauea increases, the age of the rocks increases. All right, so that's today's lesson about hotspot. You should have a test wizard on this, I believe. You can go check it out.